Hello, everyone. I'm reminding you that we are continuing the set of lectures within the Department of Postgraduate Studies of the Viktor Glushkov Institute of Cybernetics of the National Academy of Ukraine. The course name is Server of Optimization, and today we are in lecture 7. So the course developer is Butenko Sergey, professor of taxes A&M University. Course advisor is Petsyuk Pyotr Ivanovich, Doctor of Sciences, Institute of Cybernetics. And the course instructor is Valeria Ivana, who represents the Institute of Cybernetics too. So today we continue our topics regarding mathematical programming and specifically the Simplex method of solving LP, which was first introduced in the previous lecture and will be extended to other actual cases in LP. The agenda for today's class, we will just review. I will remind you the major methods of solving LP. Then we will shift to the issues related to recognizing optimality and specifically recognizing optimality principle. Then we will consider the cases of recognizing unbounded LPs, also the cases of degeneracy and cycling. With this respect, we will go on with properties of LP dictionaries and the Simplex method. Also, we will refer to the heavenly pouch incorporated problems modified with modified constraints, and again, still solved using the Simplex method. And also, for some cases, we will consider big M and two-phase Simplex method as a further extension over the Simplex methods first developed by Danzig. Okay, so I'm just reminding you, we discussed it in the previous lectures, that the major method of solving LPs actually involve the graphical methods, which is mostly used for two variables, and this is the topic which has been already covered. The substitution method, the linear combination method, the Simplex method, which is actually the key of our interest for now, Hachi-Yan's algorithm based on polynomial time solvability of linear programs, also the ellipsoid method introduced and developed by Noam Shor, in Karmakar's algorithm, which refers to an integral point method. So last time we stopped at the heavenly pouch incorporated problem, which was solved using the Simplex method before we solved it graphically. Even earlier, we solved it using the solvers and the AMPL actual program. So now we are discussing actually the possible cases of solving actually the same problems with different variations. But so far, we stopped the iterations at step 2, and here actually the slides represents the step 2 dictionary and the step 2 tableau. And here we see that first, all of the variables have negative coefficients, right? So meaning that there is no potential for optimality furthermore. Well, and here in the tableau format, we see that all of their coefficients, which are non-zero coefficients, they are positive here. Recall that the coefficients in the tableau format appear with the opposite sign. So, and using both step 2 dictionary and step 2 tableau, we can conclude that 9,375 for this objective function is the optimal value with the number of products produced of 125 for product 1 and 300 for product 2. And the basic solution, okay, and the basic visible solution is represented on this side. So no, we ignore the slack variables here. The slack variables, when we report the final solution, because no, the slack variables, they are not included in the original problem. So that's why we can actually ignore them. So how can we recognize that it is optimal? Again, so we will just sum up. No, again, S sub 1, S sub 2 are non-negative. Remember that because it is a mass constraint. Then the highest possible Z is obtained when these values are zeros. No, and as I said, the slack variables are ignored since they are not a part of the region A. So, and here we come to the main principle of recognizing optimality. If in a feasible dictionary, all non-basic variables have non-positive coefficients in the zero, then the corresponding basic feasible solution is an optimal solution of the. In the tableau format, everything goes into the opposite sign because we consider the difference between the z and the right-hand side of this. So when we use the tableau format, then the basic feasible solution is optimal if all non-basic variables have non-negative coefficients in row z, 0, and the corresponding tableau. So here we have non-positive, here we have non-negative. Yeah, recall that actually they have opposite values. Now let's consider the following example. What we have here in this dictionary, we have two variables, original variables in the objective function, and we have one free coefficient. Since this one is negative, so this is the only positive actually coefficient in the objective function. So therefore, x sub 2 is the only entering candidate in this LP. Then for the leaving variable, yeah, we cannot really determine it because all the coefficients in the corresponding column are positive, but according to the simplex method as it was introduced by Danzig, it needs to be at least one negative. So therefore, if they're positive, so and x sub 2 is increasing, then z is increases to positive infinity. So they will definitely, if we increase it without any limitations and here, so then z will eventually reach actually the positive infinity, meaning that the problem is unbounded. The phenomena of being unbounded, for the solution being unbounded was discussed in the previous lectures, meaning that we have an infinity many solutions for this problem. No, and but the same thing actually is recognized in a tableau format, and it looks like this. Again, all positive values change into negative, or positive values change into negative, and negative values change into positive. Okay, because we consider the difference between z and the right-hand side of this inequality. So that's why actually the signs are changed. No, that was discussed actually in the previous lectures. So recognizing unbounded LP's principle. So if during the execution of the simplex method, we encounter a variable that has all non-negative coefficients in the dictionary format, then the LP is unbounded. In tableau format, an LP is proved to be unbounded and bounded as soon as a column with no positive entries is detected. Now, let's consider another example. To maximize the function which contains 4 variables with 2 constraints referring to the expression and 1 non-negative constraint, where x sub 5 and let x sub 5, x sub 3 be slack variables, no, because we have the less than or equal inequality relationship, and so therefore definitely slack variables will be used. But what is here specific? We have 1, 2, 3, 4 variables and 2 constraints. One thing is specific, then another thing is specific. Actually, an interesting feature that can be seen about this problem is that the right-hand sides are all zeros in this case, meaning that we do not have free coefficients here. Now, what we receive. So as we write it in a tableau format, their signs change. The signs the signs change. So here we have, so this is actually step 0 tableau format. Then both basic variables, if both basic variables are equal, basic here, basic variables are equal to 0 here, right? And then actually what is interesting, everything is 0 here. So then according to the dancing rule, according to the simplest method rule, we select the coefficient with the lowest negative value. But here, in fact, if we apply the ratio principle, so for us to find the winning row, the both ratios will be 0, because there are zeros here. So, but we will select actually this one just because it appears first. So therefore, the 1, 4 corresponds to the entering variable and to the leaving variable. So pivot variable and pivot element. What we have then? No, by using the rules, we enter x sub 1. X sub 1 enters, but actually the right-hand side doesn't change. It remains 0. So the basic feasible solution is the same as at step 0, even though the basis has changed. Here the basis was x sub 5, x sub 6, but here it is x sub 1, x sub 6. Now let's continue actually the iterations and we will see where it will lead us. No, first of all, when the basic solutions with 1 or more basic variables equal to 0, they are called degenerate. Now let's see if we continue with iterations, what we will obtain at the end. Now let's perform step 2. Now here again, negative 13, it's only 1, by the way, negative 13.2. Here the both are zeros. Now we select actually the positive one. It is 1/10, and we keep on working. And again, we receive new BFSs, x sub 1, x sub 2, and still actually zeros come in the right-hand side, meaning that the basic feasible solutions haven't changed again, even though we actually changed the variables, but solutions haven't changed. And 0 remains actually the value for the objective function here. Now, an iteration of the simplex method, which results in a new basis, well, here is the new basis, with the basic feasible solution that is identical to the previous basic physical solution, is called a degenerate iteration, and the corresponding phenomenon is referred to as degeneracy. Now, let's keep on working. We keep on working further, 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 and further. And finally, we come at step 6. We come to the table, which is exactly the same as we had at step 0. Meaning that if we start all over, we will repeat the same steps from 1 to 6. Thus, if we continue with the execution of the simplex method, we will keep repeating the calculations performed in steps 1 through 6 and will never be able to leave the same solution. The definition: a situation when the simplex method goes through a series of degenerate steps and as a result revisits a basis it encountered previously, is called cycling. So this situation is called cycling. But the good news is that there are ways to get out of this trap, and there are several approaches of how we can avoid cycling, though today we will mention only one, which is no, the most simple, I would say. No, the method is referred to as Bland's rule. A little bit about the author, some historical background. So this method was developed by Robert Bland, and actually it is named after his name, an American researcher and professor, who, in fact, no, as far as I remember, actually had the Belgian roots. And the topic was introduced in this method was introduced in 1977 by publishing his article, New Finite Pivoting Rules for the Simplex Method, in the edition in the Journal Mathematics of Operations Research. So this is actually when this method was introduced. No, and the rules, the algorithm of this algorithm is the following. But remember that with Danzig, we selected for pivoting variable and for leaving variable. No, for pivoting variable, actually, we selected the one which had the highest positive coefficient if we speak about dictionary format, or the lowest negative coefficient if we speak about blue format. Yeah. And for the leaving, for the pivoting element, for the leaving variable, we selected the one which satisfied the smallest ratio actually test. So, so here we will take another track. So we select the entering variable by choosing the smallest index of non-basic variable whose simplex direction is improving. Then we select the leaving variable. No, entering is the pivot variable. Remember that for the leaving variable, so which corresponds to the pivot element, we select the smallest index from those that define the maximal step size. So we just follow the simple rule, and if we follow this simple rule, we can avoid cycling, as the theorem on the next step says, or the next slide says. So according to the theorem, if Bland's rule is used to select the entering and leaving variables in the simplex method, then cycling never occurs. Now let's refer to the same tableau which we considered before, with the example which considered before, at step 5. So what did we get previously at step 5? In the 0, we have 1 for the z coefficient. Then for x sub 1, we have the coefficient -6. For x sub 2, the coefficient -9/2, 39/2, 0, 0, -10, 0, 0. According to the previous actual rule which we used, which we applied, we should have selected -10 for the pivoting variable. Yeah? But here, the candidates for entering the basis are x sub 1, x sub 2, x sub 3. And according to the rule, we just select the first one. Yeah, because it appears first in this series. Then, for the as for the leaving variables, the only candidate of the leaving variable is x sub 4. No, actually, we do not have any choices, just because 1/2 is the only positive coefficient. So therefore, here, actually, we do not really need to choose it. It's just 1. So therefore, by applying standard simplex method steps algorithm, we obtain the following table. Here it is. And here we have, what do we have? That there is only one candidate for the entering variable. It is this one. And there is only one variable for the leaving variable. It is this one, x sub 1. So x sub 2 goes for the entering, x sub 1 goes for the leaving variable. Yeah? So, and here by applying the Simplex method, actually we come up with the optimal tableau format. And how do we know that it is optimal? We see that all the coefficients in the zero are non-negative, so therefore the optimality criteria is satisfied. No, and in fact, we still have the same solution because there are all zeros now, but the difference with the previous and this one is that, no, what happened here? We started with the optimal solution, but the interrelations which we performed before didn't allow us to see that it was optimal because the optimality criteria was not satisfied. So, but by following the blank rule, we have arrived to the objective where all the coefficients are non-negative in the dictionary format, and actually this fact proves the optimality. So the last tableau proves the optimality that z is equal to 0. So therefore, we've just justified this value as the optimal one, and we stopped, actually we terminated the iteration. So by doing this, by solving the example so far, we have realized that there are potential issues in performing the Simplex method. No, the word issues can be replaced by the popular word challenges or unpopular word problems, which is considered to be not politically correct. So therefore, we will replace it by the word issues. So which issues do we have at the three major steps in the Simplex method, which are initialization, iteration, and termination? No, for initialization, the problems which might occur are the following. Will we always be able to start, and how to find the starting feasible dictionary? With iteration, can we always choose an entering variable, find the leaving variable, and construct the next feasible dictionary by pivoting? And for the termination, again, remember the termination mostly deals with cycling. Is there a possibility that the Simplex method will construct an endless sequence of solutions without ever reaching an optimal solution? So this is a cycling issue. Now, which ones have been already discussed, and actually the methods were introduced? That is for termination. Yeah, so the Black's rule actually helped them to get out of cycling. Now let's consider the iteration issues, which are how we always choose an entering variable, find the leaving variable, and their solutions actually. So how the ways actually to handle these issues at the stage of iteration are based on the following properties of LP dictionaries and the Simplex method. No, property one: any two dictionaries of the same LP with the same basis are identical. So any two dictionaries with the same basis must be identical. No, and here we actually introduce the very simple and short proof of it, which ends up actually with this result. The next property, again, which guarantees the feasibility of finding the starting and leaving variables. So at the stage of iteration is property 2, that every solution of the set of equations comprising the dictionary obtained at any step of the Simplex method is also a solution of the step 0 dictionary, and vice versa. So the initial dictionary is a linear system that represents the original LP written in the standard form, and the only transformations actually we apply to this linear system at each iteration are elementary row operations, which were used even in linear algebra. So to express the new set of basic variables through the remaining variables. Since applying elementary row operations to a linear system results in an equivalent linear system, this property is true. So which you might remember actually from basic matrix operation. And property 3 refers to, again, to the feasibility issues. If step 0 dictionary is feasible, then each consecutive dictionary generated using the Simplex method is feasible. So the ratio test is used to determine the leaving variable at each step and is designed to ensure that the constant term in the right-hand side of each equation is non-negative, so that setting all the non-basic variables to 0 yields non-negative values for all the basic variables, and that the corresponding basic solution is feasible. So thus, if we start with the feasibility dictionary, feasibility is preserved throughout execution of the Simplex method. It actually proves our statements on property 3. So we have discussed the iteration actually issues, how they can handle. No, and with our concerns about the termination. So the Simplex method may go through some consecutive degenerate iteration with no change in the objective function value, in which case cycling can occur. It appears that this is the only case where the method may not terminate. No, there are 2 termination criteria that we discussed before. So the theorem states that if the Simplex method avoids cycling, it must terminate by either finding an optimal solution or by detecting that the LP is unbounded. These are the 2, so and actually the optimal solution or being unbounded actually are 2 termination criteria that we have already discussed. And now imagine that every step we perform in the iterations method. At every step, we start with selecting an entering variable and then selecting a leaving variable. And we said that if we cannot select an entering variable, this means that we reached the optimal solution. And if we cannot select a leaving variable, it means that we proved that the problem is unbounded. But if we can select both entering and leaving variables, then we proceed with the iterations, and while performing the iterations, we go through the set of feasible solutions. So the basic feasible solutions are uniquely determined by the selection of the basic variables. We express basic variables through the non-basic variables. So the way we get the basic solution, which we encounter while running the Simplex algorithm, we can have at most the combination of the combination of n plus m taken by m different ways of choosing a set of m basic variables from the set of n plus m variables. N actually refers to the number of original variables. Since any 2 dictionaries corresponding to the same basis are identical, there can only be a finite number of the Simplex method steps that are different. So therefore, if the Simplex method does not terminate, it must eventually revisit a previously visited basis, meaning that cycling occurs, but we know actually how to handle cycling. So the only issue, so we have actually addressed how to handle the iteration issues, the termination issues. So the only issue that we need to address is initialization. So let's see what kind of problem we can see with this stage, and let's consider the following example, which again refers to Heavenly Pouch Incorporated. And recall that we were talking about a manufacture of carriers, and so the objective function which was formulated before is to maximize the profit. Also, we had solid color fabric constraint, printed fabric constraint, budget constraint, demand constraint, and of course non-negativity constraint. Now we add one more constraint, and which relates to the number of carriers allowed to be made, and they are at least 100 carriers can be made, and this constraint is expressed as the a new inequality, by the way, included into the model, x sub 1 plus x sub 2 greater than or equal to 100. Recall that this inequality sign refers to the words at least. And what do we have now? As the result, while introducing it, no, actually, okay, let's go the standard way so far. So remember that for the standard simplex method, first we introduced slack variables, but here we have a flipped inequality relationship. So therefore, we will have an excess variable and we will subtract it. Now, let's do it and convert the given LB to the standard form. So, and here it is 1, 2, 3, 4 slack variables and 1 excess variables. Remember that all of them need to satisfy the non-negativity constraint. So as the result, while introducing everything in a standard form, we eventually determine that dictionary format, if determine that x sub 1 and x sub 2 are equal to 0, then this equation results in negative 100, which is less than 0, which is negative. It means that we come to infeasibility. So if we come to infeasibility, we cannot initialize the simplest method with this dictionary. What shall we do? How to overcome this obstacle? Now, let's discuss two variants of the simplex method designed to overcome this obstacle. And here are the two methods, not rules, the two methods, the big M method and the two-phase simplex method. The both methods are based on a similar idea of introducing an artificial variable for each constraint, where the starting basic variable, such as the slack or excess variable, is not readily available. Let's discuss those artificial variables. Now, one potential solution is to introduce an artificial variable for each constraint where such as slack or excess variable is not readily available. For example, what this constraint corresponds to constraint 5. Yeah, it was here. Constraint 5, where is it? Here, constraint 5. Then for this constraint, we introduce artificial variable. Here it is. We denote it as a sub 5. Again, it needs to satisfy the non-negativity actually constraint. And the idea is such that at the end, we need to make sure that this artificial variable is equal to 0. Then we may say that these expressions are equivalent. I think it is open. If a sub 5 is not 0, then it will violate this original constraint. And no, it is not actually a good thing. So if it is negative, again, it will violate the initial constraint. Yeah. So therefore, we need to somehow minimize the variable a sub 5 and make sure that eventually it will become a 0. So in this case, the modified constraints will become exactly the same as the original one, as this one, and it will be satisfied. So the both methods utilize alternative ways of driving the artificial variables out of the basis, eliminating them somehow, thus ensuring that they all eventually vanish whenever LP is feasible. Now, one approach is to explicitly minimize a sub 5 whenever actually we have a constraint for which I need to introduce the artificial variable. So, or we minimize the sum of all artificial variables and make sure that the minimum will be equal to 0. The other approach that we'll use instead of the sum of artificial variables explicitly will try to penalize the non-zero values for artificial variables by adding these artificial variables to the objective with particular coefficient, and will penalize having non-zero values for artificial. So we will illustrate these both approaches on the same example. Now, let's start with big M method algorithm, which has several steps as the following. Step 1, modify the constraints so that the right-hand side of each constraint is non-negative. So this requires that each constraint with a negative right-hand side be multiplied by -1. So remember that if you multiply an inequality by any negative number, the direction of the inequality is reversed. So after modification, we identify each constraint as greater than or equal, or less than or equal. So step 2, convert each inequality constraint to standard form. If constraint I is less than or equal, so we add a slack variable denoted as sub I. And if the constraint I is greater than or equal constraint type, we subtract an excess or surplus variable E sub J. E sub I, yeah, I. At step 4, we add an artificial variable denoted as A sub I to the constraints identified as greater than or equal at the end of step 1. So also we add this sign restriction for non-negativity of the newly introduced artificial variable. So then step 4, this is what makes big M method different from the other one. Let M capital or M big denote a very large positive number. So if the LP is a minimization problem, we add M times A sub I to the objective function, which was before equal to 0. If the LP is a maximization problem, we add negative M times A sub I to the objective function. Step 5. Since each artificial variable will be in the starting basis, all artificial variables must be eliminated from the objective row before beginning the simplex. Now solve the transform problem by the simplex and choosing the entering variable. Remember that M is a very large positive number. If all artificial variables are equal to 0 in the optimal solution, we have found the optimal solution to the original problem. If any artificial variables are positive, the optimal solution, the original problem is infeasible. So let's go on. Let's consider the example. So this is the flow chart of this method, and we move to the example in which we have a maximization example, in which we have 3 variables. We have 3 constraints. 2 of them are greater than or equal times. 1 of them is less than or equal time. And we have also a non-negativity constraint for this model. So again, at step 1, as it was said before, we subtract the excess variables and add for the constraints which contain greater than or equal relationship, and add a slack variable for the constraint where we have less than or equal relationship. So, and here we have for the constraints, the maximization of the objective function stays the same. For the constraint, for constraint 1, we have -2 times x of 1 plus 3 times x of 2 plus 4 times x of 3 minus x of 4 equals 12. So here we subtracted an excess variable, x of 4, newly introduced. Then 3 times x of 1 plus 2 times x of 2 plus x of 3 minus x of 5 equals 4. This is another excess variable which is subtracted, notice as x of 5. And x of 1 plus x of 2 plus x of 3 plus x of 6 equals to 9, where x of 6 is a newly introduced slack variable denoted as x of 6. So therefore, the constraint for non-negativity extends for all the axes with the indices from 1 to 6. So the basic solution with the basis consisting of x of 4, x of 5, and x of 6 are infeasible. Now let's introduce artificial variables for the first two constraints, a sub 1 and a sub 2, and the corresponding problem is referred to as auxiliary problem, and it can be written as a maximization problem. Now, initially, in fact, we dealt with minimization of the sum of the a sub 1 and a sub 2, but any minimization can be converted to maximization just by putting a minus sign in front of the expression. So therefore, minus a sub 1 plus a sub 2 is the same as minus a sub 1 minus a sub 2, and so far all the other terms of the objective function have been crossed out. Yeah. Now what happens to the constraint? Here we add a sub 1. So the right-hand side remains the same. Here we add the other artificial variable a sub 2. Here we do not add anything because we had the relationship of less than or equal, but here we had greater than or equal. So that is actually the issue. So the objective function of the auxiliary problem is always non-negative. Thus, any feasible solution of this problem with a sub I equals 0 is feasible. The big M problem associated with LP given by the expression of the objective function and the auxiliary part multiplied by M. If a feasible solution for the big M with a sub I greater than 0 for at least one I exists, then the objective function value can be made arbitrary poor or very large by selecting a sufficiently large constant M. Again, M is a non-negative constant, which you make it as large as you want. Then the step 0 tableau format. No, first of all, let's return how we in fact came to that. The initial tableau format before step 1 comes from here. From here. So here what we have for the first row, for 0, we have -1, 2, 3, 0, 0, 0, M, 0. Yeah? Then we have 2, -3, -4, 1, 0, 0, 1, 0, 12. Then we have -3, -2, -1, 0, 1, 0, 0, 1, 6, and -1, 1, 1, 0, 1, 0, 0, 0, 9. Okay, so that is actually the initial one. Yeah? For us to come to step 0 tableau format, and then remember that non-basic variables are in the objective. So, and for basis now, at this point we have A sub 1, A sub 2, and S sub, and this one, X sub 6. Yeah, with this positive, positive, positive. Yes, we have that. Okay, so what we need to do, we actually need to make them 0 at this point, but initially they had M. How do we do it? We multiply row 1 and row 2 by negative, and it was M, yeah? By negative M, and then add both results to row 0, yeah, to the objective function 0. After doing this, we obtain with this step 0 tableau. And what we have here, we have this one and this one are zeros, that is good. Then we remember that M is a parameter which approaches 0. So while comparing two basic variables, coefficients involving M, the coefficient with the greater multiplier for M is considered greater. The most negative so we need to actually choose the entering and the leaving variable. So the most negative multiplier here is -5M minus 3. So therefore, it is a candidate for the entering variable. Now here, apply the ratios. We have 4, 1, 1, so they are all positive. So 12 divided by 4 is 3. 6 divided by 1 is 6. 9 divided by 1 is 9. So therefore 3 is the minimum value of the ratio. So therefore A sub 1 is the leaving variable from the basis. So that's why we selected actually this quadrant. Then we update the objective function. How we update it, please review it again from the previous lecture or from the textbook actually. So because there are a lot of computations and they just cannot be included into the lecture. So therefore, this is what you can work out on your own. And by performing the traditional Simplex methods and going through step 1, step 2, step 3, step 4, we come up with the optimal tableau. It is optimal because all the coefficients are non-negative here. Okay. Then we have the only one basic variables from the original variables. It is X sub 3 with the value of 9. The X sub 1, X sub 2 values are not included into the basic one, meaning that they are 0. And the Z value, so the maximum objective value, function value obtained, which can be obtained, optimal one, is 27. So the optimal solution is X sub 1, X sub 2 is 0, X sub 3 is 9, Z is 27, as the variables x sub 4 and x sub 5 were slack variables, so they were not included into the original problem, and the model actually ignores these values. Now, the two-phase simplest method algorithm actually is no, for the first three steps actually is very similar to what we did for the big M method. No, the historical background is such that it was introduced by Ulunwu and Tenham in the early 90s, in the first half of the 90s, by issuing an article called the two-phases method and efficient procedures to solve by objective combinatorial optimization problem. Yeah? So it was published in 1995, but no, I believe that the method itself was introduced era. So they're both Belgians and they work for university, and hopefully they're still alive. So the steps actually, the steps which they suggested actually for this method are the following. Step one, we modify the constraint so that the right-hand side of each constraint is non-negative. So this requires that each constraint with a negative right-hand side be multiplied through by -1. We identify each constraint that is now greater than or equal constraint. In step 3, an artificial variable will be added to each constraint. So convert each inequality constraint to the standard form. If constraint I is of negative than or equal type constraint, then add a slack variable s sub I. If constraint I is greater than or equal constraint, then we subtract an excess variable e sub I. So at step 4, if constraint I is greater than or equal constraint, we add an artificial variable a sub I. For now, we ignore the original LP's objective function and instead solve an LP whose objective function is the minimum W sum of all the artificial variables. So this is called the phase 1 LP. The act of solving the phase 1 LP will force the artificial variables to be 0. And because each artificial variable a sub 1 is non-negative, solving the phase 1 LP will result in one of the following three cases. No, case 1, the optimal value of W is greater than 0. In this case, the original LP has no feasible solution. Case 2, the optimal value of W is equal to 0 and no artificial variables are in the optimal phase 1 basis. So in this case, this is actually what is very good. We drop all columns in the optimal phase 1 tableau that corresponds to the artificial variables. So we now combine the original objective function with the constraint from the optimal phase 1 tableau. This yields the phase 2 LP, the optimal solution to the phase 2 LP, the optimal solution to the original LP. And case 3 is such that the optimal value of W is equal to 0, that at least one artificial variable is in the optimal phase 1 basis. In this case, we can find the optimal solution to the original P if at the end of phase 1 we drop from the optimal phase 1 tableau all non-basic artificial variables and any variable from the original problem that has a negative coefficient in objective row of the optimal phase 1 tableau. So therefore, in short, if W is greater than 0, it corresponds to the situation when the original LP has no feasible solutions, and when it is equal to 0, then we believe that the original LP has at least one feasible solution. Now, more detail about what we will do at the phases. So at phase 1, we saw the auxiliary problem, and as a result, either obtain a feasible tableau for the original problem with the optimal objective value is 0, or conclude that the problem is infeasible if the optimal objective value is positive. So at phase 2, if the problem was not judged infeasible in phase 1, we solve the original problem using the optimal tableau of the auxiliary problem to get the starting tableau for the original LP. So now let's perform it. So for comparison, we apply this method to the same example, again with three decision variables, then three constraints, one non-negativity constraint, then two of the constraints are of greater than or equal type, and one constraint is of less than or equal type. So according to the rules, like as it was stated before, if it is greater than or equal, then we subtract additional variables denoted as x4, x sub 4, x sub 5, x sub 6. Also, we subtract x sub 5 from the second constraint, and for the third constraint, as it is of less than or equal type, then we add x sub 6 to this inequality in order to obtain their equation. So, and again, we add that all these variables, as both original and newly introduced, are greater than or equal to 0. So the basic solution with the basis consists of x sub 4, x sub 5, and x sub 6 is infeasible so far, because here they are like negative. Yeah, if all these are negative, it means that here we come to, no, these ones, yeah, we come to negative values, which contradicts actually the initial constraint of being non-negative. Now let's apply phase 1 OP. So at step 1, or at phase 1, before we proceed with the method itself to the tableau, we express the objective through non-basic variables. Recall that we speak about auxiliary one. Just I will show you where it is. Where is it? Auxiliary one. Oh, here, yeah, auxiliary one, yeah. So that's why we put down z minus this expression. We have z equals negative a sub 1, negative a sub 2, yeah, or z minus. So, no, and then we substitute the values for a sub 1. So, and here is one of them, and here is the other one. We would get them from the constraint, from here. Where is it? I will show you. Where it comes for at home, you can actually, from here. They come from here. Okay, no, then we just perform simple arithmetic operations. Please practice it at home yourself, find the like terms, and end up with the following objective function. Negative 18 plus x sub 1 plus 5x sub 2 plus 5x sub 3 minus x sub 4 minus x sub 5. Next, we set up the initial tableau of phase 1 after eliminating artificial variables from the 0. You see that they are all zeros here, yeah? No, and here is a table, yeah? No, then we apply the standards as the Danzig rule, yeah? So this the most negative value, which is negative 5. Then we find the ratios, and here it is 4, here it is 4, here it is 3, and here it is 9. So the lowest is 6 divided 3 out of these ones. So therefore we select this one actually for the living variable. So this is the living variable. So this is the pivot row, or the pivot row. This is the pivot column or the pivot variable. Then we update it, and then actually the computations, I recommend you to perform the computations at home yourself. We will just quickly go over them. So then we apply simplex iterations to step 1, step 2, and finally, actually, we get the optimal one. How do you know that it is optimal? That just because there are no negative values here. So therefore, the basic variables appear to be x sub 3, x sub 2, and x sub 6. And then we drop the columns for the artificial variables in the tableau above and replace the basic variables x sub 2 and x sub 3 in the objective function of the original LP. Again, why x sub 2 and x sub 3, but we do not actually care about x sub 6 because x sub 6 was a newly introduced variable. It was a slack variable. No, and the values were found here. Then we substitute, find the like terms, perform basic arithmetic operations, and this is the updated objective function. And we move to phase 2 after eliminating x sub 2 and x sub 3 from the 0. And the updated step 0 tableau for phase 2 looks like this one. So what is here? Now, the good thing is they are known 0 here. Here they are 0, yeah, because we eliminated, actually that was our goal. There are no artificial variables here. The good news, we have actually got rid of them. No, and then actually go on with applying the simplex method further. So that is step 1. Result, please at home work them out yourself. You can watch the video if you have forgotten how to do that. Then the previous videos, I mean, then we perform iteration 1, iteration 2, iteration 3, and at iteration 3, we come up with the optimal solution. And it is optimal because there are all non-zero values. Then the only original variables which appears in the basis is x sub 3, and actually it has a non-zero value. It is 9, so it comes here. The optimal, the maximum z value which can be reached with the given original variable values is 27, and x sub 1, x sub 2 appear to be non-basic variables, so it means that they are 0. So the optimal solution at the end of these iterations is x sub 1, x sub 2 equals to 0, x sub 3 equals to 9, and the maximum possible value of the objective function z is 27. So thank you very much. Please, at home, I recommend you to perform the computations related to the tableau format. It is the same as the matrix actual operations. Have a very good day and success to you.